Okay, I think I'll kick off now. I think there's still plenty of people just kind of straggling at the end. So, good morning, everybody. Hope you're enjoying yourself so far. My name is John Cunningham. I'm a developer in the Visual C++ debugger team at Microsoft. And this talk is going to be on power debugging techniques with Visual C++. So I think we should get it out in the open just now that I do have a slight accent. Yes, it's true, I'm French. No, are there any other Scottish people in the audience? Any other Scots? No, that's okay. So I can take the mickey out of Scottish people for the whole thing without being lynched by my countrymen. So it's time to build the business internet by debugging Visual C++ programs, obviously. So the standard disclaimer that comes with this talk is that many of the things that I'm going to be talking about are undocumented, they're unsupported, and that if you phone PSS up and say, hey, John Cunningham told me this would work, they're going to go, who? They're untested by our QA people. They might not work quite as expected, and they're definitely only working in Visual C++. And they may change in subsequent service packs or other versions. So you know the solid foundation that these present. So a quick rundown of what you can expect to find out about in this talk. The little radiation signs don't mean that you're going to melt down when you use these functions. It's just that these ones are the specific ones that are not documented. So I'm going to talk a little bit about autoexp.dat, which is a file which can help you debugging enormously, expands types and so on. A little bit about not stepping into functions that you don't care about, function evaluation, some multi-threaded debugging. Now, by that I mean debugging cases where you have particular problems to do with deadlocks, thread timing issues, and so on. Some discussion of naming of threads. Some stuff to do with exceptions. I'm sorry, but someone has moved my radiation sign. That radiation sign should be next to thread names. That's the actual thing that's undocumented. A little bit about breakpoints, a little bit about memory corruption. Discussing optimized code and how to debug it specifically. Casting to types, something about the modules window, and some common complaints on the right-hand side here. Debug works and release doesn't. It works when I don't use the debugger. Something to do with how to time your code from the debugger. A little bit about edit and continue. Again, these things have been moved slightly, so timing code and pointers as arrays. I'm sorry I didn't check the ones on this machine, but timing code and pointers as arrays are the actual ones that are undocumented, not edit and continue and disassembly tricks. So edit and continue, which is a well-documented feature. Pointers as arrays, which you may not have come across before. Some tricks to do with disassembly, dealing with strings in Unicode. I'll go over remote debugging scenario, how to make that easy on yourself, and a little demo at the end to do with COM debugging. And smarter through this, I'll be working through a small demo just to show some of the features that I'm going to be talking about. Now, I don't know if any of you have had a chance to have a look at the PowerPoint slides that are on your CD, but there is some sample code that comes with these slides, which I'll go over in depth at the end, and some pointers to where you can get some more info, and discussion, which is the usual Q&A at the end. So if you've got any specific questions, debugger questions, if you could hold off till the end and queue up at the microphones at the end, and we'll get a good discussion of whatever you need to know. So we'll move swiftly along then. autoexp.dat. It's a text file that lives in the msdev.exe directory, the bin directory under common msdev. And what it does is allow you to immediately display information about custom types in the watch window, the quick watch window, as you hover over things in your data tips and things. And I've got written down C actual file for documentation because it's the best source. So I think I'll switch over and introduce you to my small demo sample at the moment, if I can work the AV equipment. So I got a small demo here which talks about Scotsman, which is quite handy. As you can see, Scotsman is derived from the class man. Scotsman fall into 4 distinct groups. All Scotsmen fall into these 4 categories of heroes, kings, inventors, and debugger developers. And you can see there's a couple of methods on Scotsman. They have a Boolean method is a drinker, and you can tell them to drink too much as well, which is quite handy. So if I debug my little application here, which I've written, which is create some Scotsman, as you do, some on the heap, some on the local stack. Tell the Scots to go and have a drinking match, which is quite a common occurrence as usual, and tell the Scots to go and change a light bulb. We'll get to the answer to that question eventually. So if I step into this code with the debugger, we can see that I'm watching the 4 values for the Scotsman as I create them. Now, in the watch window here, you don't get an awful lot of information about the particular objects until you expand them. So if I am interested in who Scotsman 1 is, I have to open him up, find out that he's a hero, then drill down and find out what the name of the man is, and eventually I find out that he's William Wallace and he's a hero. And if I actually want to look at more than one, you can see I end up using quite a lot of real estate to make that happen. I've only got 4 values, but I end up taking up almost the full screen just to be able to compare what's in those 4 values. So if we switch over to autoexp.dat, expand this here. As in all the best demos, here is one I managed to cook earlier. So a quick rundown of what this line is saying in autoexp.dat. It says that whenever you come across the type Scotsman, print out for me, please, the name, or what's in the name actually, as a string, and also what type of Scotsman he is. So I've uncommented that. I'll save that back out. Now, autoexp.dat is reread every time you start debugging. So we'll compare this session now to what I had last time. I step in, and this time, as I step through, each of the Scotsmen gives you the full information about them, and I save all of this real estate by showing that information in the types, which is very useful when you've got complicated types and you want to quickly identify which object you've got. You can see very quickly there. And that's how you can get to that information. So as I said, most of it is actually documented in the file. One thing you have to remember about what's on the left of autoexp.dat, telling it which type you want to expand, you have to give it the real type. So the debugger doesn't know about type defs. If you've got type def foo pointer as a foo star, the debugger really wants foo on the left-hand side. As I said, it's reloaded at debug go time. So if you don't quite get the expansion, I'm sorry, if you don't quite get the expansion that you're looking for on the object type, then it's easy to play around with it, experiment with it, format it exactly the way you want just by go, start, stop, go, stop, go. And that covers that section of autoexp.dat. So moving along, another part of autoexp.dat, another section, is a feature which allows you to not step into specific functions. This is really quite useful for when you have a lot of glue code or a lot of temporary objects that are created. You know, I tend to, when I'm stepping through code, use F11 to step into. You know, you want to drill down and find out interesting stuff about what's going on in your program. But generally, you're not really interested in glue code or C-string constructors or whatever. And this section of autoexp.dat allows you to say, look, I'm not interested in this function. When I do step in, never step into these ones, step into the other one. It specifically helps when you perhaps have functions that you don't realize you're about to step into. Say, the arguments to one call are actually the results of other calls. You know, the parameters for that call are calls themselves. Then you can select to not step into them by changing this file. This is an undocumented feature, as you can see. So what you need to do in this case, unfortunately, is every time you want to change anything to do with execution control, this section, you need to actually shut down MSDev to allow it to reread it. It's unfortunate, but that's unfortunately the way it is. So you can see that I've got some statements there about which sort of syntax we can accept. You can add lines like a specific function name equals no step into, and you'll never step into that one. Or you could give it a class name, : star, and that means for every method of that class, never step into. Never step into cstring : star, for example. So a couple of examples that perhaps would be useful to you. Like I've said cstring. Definitely, if you're an MFC developer, you want to go through the MFC functions that you never care about and pop these into this section of your file. ATL as well. I'm a big fan of ATL, but I'm not particularly interested in all the glue code that's written by the ATL devs, so it's easy to filter all of that out by giving ATL : star. So a few caveats though on that. It's based completely on the function name. We don't accept parameters in that, so if you've got specific overloads that you're not wanting to step into, we're not going to be able to help you there. You're just going to not step into them all or step into them all. But it's not specific to any functions that we've written. It works on all of your functions. And like I say, it's only read on the startup. So again, I think I'll give you a quick demo of how that works. So we're back to autoexp.dat and a little chunk of execution control that I've pre-cooked as well. So I've said here that I'm not interested in any of the base class man methods, man : star, and I'm not interested in MFC's operator new that it overloads when I step in. So when I step into the constructor, I'm on the line of constructor, I will definitely step into the constructor. So before I change that, actually, I'll show you what would happen. Let's stop debugging and start again. So I step down to the first Scotsman, and if I step in here, oops, if I step into the one that's allocated on the heap, I should say, you'll see that I step into the operator new, which is, well, woo, it does a malloc, hurrah. And I have to step back out and step back in again before I get to the constructor of Scotsman. So I'll stop debugging, quit out of this just now. And let's take this section and copy it into the autoexp.dat file. So again, let's step down to the constructor, to the allocation on the heap, and this time, straight into the constructor. No more glue code in your way. And this time as well, if I press F11, as I just did there, I don't step into the man constructor, which I would have done in the previous case. Which hopefully will be quite useful for you to get rid of too much stepping when you're doing your debugging. Managed to trip over this little cable so much. Function evaluation. So the debugger has the ability to call any function in your program at any time by you typing that function name and any parameter you want into the watch window. It's particularly useful when you've got a complicated structure that you want to quickly, show me how this complicated structure is. You know your structure yourself. The debugger's a bit stupid. It knows how the type's laid out. But if you've got complicated collections or so on, then you can quickly write a function that iterates over them, dumps out all the info about it. There you go. So to use that in the debugger, the best way is to use output debug string. I assume everybody's come across output debug string, the way to send string events to the debugger. There are some limitations, however, on this actual feature. If the function call lasts more than 20 seconds, if it goes off and does some remote decom thing, then we're going to kill it. We think it possibly is dead, so we're just going to kill it, unfortunately. If it raises any exceptions as well, we'll also say, right, that's enough of that. We'll not do this function anymore. And it only works on the thread that you're currently stopped in as well. We just take that thread over, call your function on that thread. So you can't expect to use multi-threaded stuff around this. So moving on then from threads, multi-threaded debugging. Like I say, this is specifically cases where you are debugging problems to do with threads that are interlocked, deadlocked, not debugging any program that has multiple threads. That works, thankfully. It's really hard, there's no doubt about it. It's a tough subject to track down deadlocks. One thing that can help you, however, is we have the ability to look at the thread information block at any given time. And this allows us to see the unique thread ID for this thread. Although I've got Windows NT4 here, this actually works on Win2K as well. And on Windows 9X, we can look at the FS register, and that tells you exactly which thread you are. Although it's not the thread ID in FS, it is a number that is unique to that thread. And this allows you then to set particular thread breakpoints by going to the breakpoints dialog once you've set your breakpoint and setting that condition of, as you see here, DW, which is our small macro for the D word at this address. So the D word at tib plus 0x24 is equal to 0x112 or whatever your current thread ID is. So, like I say, you want to step into your code, make sure you're in the right thread. You can get the thread ID from the debug threads window, then go set the breakpoint with this condition equal to that thread ID that you've managed to find. Thread names. So in the threads window, you sometimes see a name that we've given it. It could be some bizarre mangled name from when it managed to start from within the kernel, or it'll be the name that you started the function with if you were doing it exactly yourself. But this feature of, that I'm about to talk about allows you to set the name of the thread yourself. Now I say see set thread name in handout. This was when I believed you would each get a set of the slides. Unfortunately, you need to have a look at the PowerPoint slides that you're given on your CD for this talk. I'll also go over set thread name at the end, the actual sample. And the way that we actually do this is we allow you to raise an exception from within your program that has got a specific ID, that is the Visual C++ 6 ID. Nobody else can use that, I've been told now. And we interpret that as, we catch that in the debugger, unpack an information structure that is raised with that exception, and use the name that you've set. The maximum of 9 characters are allowed for the name. It's just the limitation we have on the structure itself. And then once you've set that thread name, all of your threads will appear with the correct names that you've set in the debug threads dialog. And that's a feature that's new for Visual C and 6 and will not work in Visual C++ 5. So exceptions, just after talking about us using exceptions. Win32 exceptions are the usual, you've overwritten some bad memory or you've dereferenced a bad pointer or something like that. If you don't handle these exceptions yourself, your app's going to die. It's going to give you that lovely dialogue saying, ah, I'm dead. And you need to handle them yourself. If you're interested in finding out where your app is raising these exceptions, if you run it under the debugger, you'll find out that we have a debug exceptions dialog, which hopefully you've all come across. This allows you to say, we want to catch exceptions, the debugger wants to catch exceptions before any handlers that are in your program gets a chance to see them. If you've got your own exception numbers as well, you can add these to the exceptions dialog and say, look, I want to be notified in the debugger of this exception number rather than my program getting a chance to see it. If you're interested in C++ exception handling, because there's only one hardware Win32 exception number allocated for C++ exceptions, to get a good stack trace of where that exception is thrown, you need to install the WinNT symbols. You'll get those on the CD that comes with Visual C++ or on the NT service packs CDs. And you need to install it into the system symbols directory. with the DLL subscript. And then in our exceptions dialog, again, you'll see Microsoft C++ exception with its specific ID number, and you can set that to stop always. So when the exception is hit, if you've said, I want to get this stop always, when you look at the call stack, you'll be able to see who's actually throwing that exception. And then what you can do to see who's catching that exception, if you're interested in somebody stealing your exceptions from you, you can step out and that'll reveal exactly who is catching that exception. So I think I've got a little demo of this again I can show you. So we're back to the Scotsman again. And you can see that when the Scotsmen go to have a drinking match, as I say, reasonably common occurrence in Scotland, each of the Scotsmen tries to drink too much. But if somebody is caught with their up exception, if someone's thrown an up, then he's caught out and he's printed out as not being able to handle his drink, which is a sin for all Scotsmen. So if I step into this, I go to the exceptions window, and since I'm using MFC exceptions, I'll change Microsoft C++ exceptions here to stop always. This will tell me if anybody is throwing an up exception, I should say. So I'll press F5, and here we go. First chance exception with the Microsoft C++ exception number has happened in scots.exe. So OK that, and it gives me the exact location in the kernel which raised that number. We're not particularly interested in that. We need to have a look at the call stack. And here we go, we can see that one of the Scotsmen drinking too much has thrown an up. And we find out, when we head down to the code, that the only time that a Scotsman throws up is if that Scotsman is a SC debugger dev. And as I say, if we step out of this now, Visual C++ says, do you want me to pass this exception on to your exception handler? Yes, please. And there it is, the exact location of the catch. A small demo, but in more complicated cases, that can be quite difficult to figure out exactly who is catching your events. Okay, I've got a reasonably long section about breakpoints. Obviously, all debuggers need breakpoints, and one particularly useful use of breakpoints is catching things other people's code who are calling into the system. My favorite of this is people are always calling message beep on me. You know, I do something in the debugger, hand it off to somebody else, and somebody calls message beep, and the thing's beeping at me all the time. Please stop beeping at me. I need to find out who's doing this. So sure, you could grep through the code and look for message beep, but I like to present the offender with a lovely rosy call stack just to show them the way in which they got there. So breakpoints on system DLLs are only available on NT. We don't have the luxury of copy on write in Win9X. We can only write into the kernel on NT. So first of all, you need to determine which DLL this particular system function you're interested in. Now, you can do that from our help system. It'll give you a guide to all the Win32 APIs and tell you exactly which DLL they exist in. Or you can look in the comma separated value file, Win32 API, which we ship in the lib directory. And that gives you a full set of information about each API, which DLL, which header it lives in. Then you need to determine the exact name of the system DLL function. Now that might seem obvious, but it depends on whether or not you have symbols installed for the NT libraries. And then you set the breakpoint on curly bracket, comma, comma, DLL name, curly bracket. Now that is Visual C++'s way of scoping things. You'll see me come back to this syntax a lot. But comma, comma, DLL name, hopefully is quite obvious. So how do we actually determine what the exact name is of any given function? So you could step into this assembly window. That'll allow you to head down into the assembly window, and there'll be a label next to the routine once you've stepped into the system function saying this is the name of this function. However, if you don't want to step into it, if you've not got DBGs for your system DLLs, you can use the dump bin utility, which we ship in our bin directory, and ask it to dump out all the exported functions for that system DLL. I've got an example here of find strict create file. You could substitute that with whichever system DLL function you're interested in. But if you are going to use the exports, if you haven't got debug information, you need to enable the load, cough, and exports checkbox in the 6.0 debugger options. If you have got symbols, it's nice and easy. You can dump in from the symbols file itself, the DBG file, and find the name of the function. So a couple of examples of those are listed here. We've got a create file. If you've got a DBG, they all look like this, underscore name at ordinal. And if you don't have DBGs, you get them with this create file A. If you're interested in setting conditional breakpoints on system DLLs, if you're bothered about who's calling message beep with this tone, what you need to do is set the breakpoint, as we've discussed before, and then look at the disassembly window. You need to have a reasonable working understanding of how arguments are passed on the stack here, unfortunately. But I can recommend an article at the end which gives you a little working of disassembly to help you out in this. And then you set the condition on where that argument is at in the stack. So again, it's DW, the D word at, the stack pointer plus 8 or minus 12 or something like that, and set it to equal whatever condition you're interested in. This one happens to be -1. So data breakpoints is possibly something that is not documented very well and people don't realize it's there. But we do try and expose the ability of the x86 chipset to watch particular memory addresses. So this is particularly useful in the case when you're looking for somebody overwriting a piece of your data, a particular object that you've created. Somebody's going and messing with it. So you can set a data breakpoint to look on that address. However, the UI, how you actually set the data breakpoints is slightly confusing. A couple of limitations. As I said, it's down to the x86 chipset that we're using. We're using specific features to do with that. And if somebody is passing your object or something like that to the kernel, and the kernel writes all over it, we're not going to catch it. And the kernel disables all the stuff as soon as you enter into it. So what we recommend is that you use the address specifically of your object. Now, the DataBP user interface allows you to type expressions for addresses in, but generally it's better to use the address so that you know exactly what address you're trying to look at, and that expression isn't re-evaluated on you and the address is moved around. So the way to quickly find the address, of course, is to look in the watch window for your object, and it'll tell you, you have a pointer to this object, here is the address of it. Then dereference that as a long star in the DataBP UI and give it the address that you're interested in. So one other thing you've got to remember about data breakpoints, since we are tied to the chip, we only allow 4 real data breakpoints. As soon as you've set 4, the next one is what we call emulated. As you can see, common confusion case, member variables causes very slow emulation. What that really means is that we're using the chip to single step through every instruction from now on, basically, to find out if the memory at that particular address has changed. So we single step, read the memory, compare. Single step, read the memory, compare. And as you can imagine, that causes an amazing slowdown. People talk about, oh, well, I've set this data breakpoint number 6, and all of a sudden the debugger hangs. Well, no, it's just taken a long, long time to single step through everything in your code. So always try and use the address to set your data breakpoints. There's some OS bugs. No, there's no OS bugs, sorry. So data breakpoints can get set permanently, then fire in other processes. That is more common on Win9X platforms than on NT. If you see that other apps are crashing after you've set some data breakpoints, definitely especially in Win9X, then it's unfortunately time to reboot. The OS isn't allowing us to reclaim the data registers the way it should. So another thing for breakpoints is that really quite powerful is setting breakpoints that only fire when they've hit a particular iteration, a count breakpoint. If you're trying to find a problem, you're going through a huge iteration of some data structure, some collection, and it crashes at a particular value, but you're not quite sure which one it's crashing at. You don't really want to break at every object that you're passing over in that iterator. You don't want to go through 1,000 of them. But it's hard to figure out what the number is. But what you can do is, if you know what the maximum number of things you're going to run round, say, I've got 10,000 listed here, it could easily be 100,000, a million. Set the breakpoint that you're interested in, but set it with a huge count value. Then wait until you crash or you get to the particular state that you're interested in, that you know is the bug. And then you can go back to the breakpoints window and look at the count value, and that'll tell you exactly how many times that breakpoint has been hit so far. And then with this advanced maths formula you can see here, you can then set the count for that breakpoint to be Cx minus 1. So one other useful thing about breakpoints is that you can set breakpoints by name. When everybody thinks of breakpoints, they're thinking line and file, but you can also ask the debugger to set a breakpoint on the start of a function. This means that, as you move stuff around in your source file, your breakpoints are going to still remain at the same start of the same functions that you're interested in. And you don't need to have to type in the full name of the function. We have a quick, easy to remember sequence of keys, which is put the cursor on the curly bracket, Control B, tab space, down, enter, enter, which I expect you all to remember as a mantra as you're heading out the door. So moving on, we're on to memory corruption. When you're using the CRT, it handily fills in particular values into memory that you're allocating or looking at to work as a guide to see what type of memory that is. So if you have a pointer and it points to some memory, and that memory is filled with FD, 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 you're off in nowhere. You've completely miscalculated your pointer, and you're just off in some memory that doesn't mean anything to anybody. If the memory is filled with all Ds, that means it's an object that you've already freed off. If it's CD, 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 it means that it's a chunk of memory you've allocated, but you haven't bothered to set any values in it. And all Cs is a new thing, and specifically to the 6.0 CRT, and that is all Cs to show you that this particular value on the stack has not been initialized as yet. If you're tracking down some heap corruption, what you can do is use the CRT's ability to try and track down heap corruption for you. But one caveat, it really is quite slow, dreadfully slow. But you can do that by setting this static variable which exists in this DLL. So in the watch window, you scope the underscore CRT DBG flag variable by saying MSVCRTD, which is the debug version of the runtime, and set that variable to 5. As I said before, data breakpoints can come in really useful in trying to track down heap corruptions. The debugger probably isn't the best tool for doing it. I mean, there's great tools out there, Numega and Rational doing great tools for it. So, these are just some helpful things to put you on the right direction. Debugging optimized code. Now, there's no great silver bullet when you're debugging optimized code. We don't have a great story here. It's really tough. But don't, whatever you do, make a hard job harder by not giving your X any symbols. Always compile with ZI. It's not going to affect how optimized your application is by the optimizer all it does is emit symbols. Generally, though, the symbols are in a particular state that's not so useful, it has to be said. Often you'll find that variables that you're looking at, you want to look at in the watch window, we don't know where they are. There's not enough symbolic information to tell us what the lifetime of any given variable is on the stack when it's been optimized, because the optimizer tends to reuse things on the stack. Line numbers can get messed up because code vanishes. You know, some algorithm that you think you've spent ages on could be duplicated in another source file in the same module, and the linker decides, we don't need that anymore, so off goes your code. So what you really need to do is, unfortunately, take the red pill Neo and look at the disassembly window, which will tell you the truth. Arguments passed to functions are normally okay, but in particular, when you use fastcall as a calling convention, if you specifically said fastcall, you might find that the stack frame for your function call doesn't exist. It's managed to get zoomed out. So the rule is find bugs in debug, because it's pretty tough to find them in optimized code. So you're interested in looking at an object in debug, but you're interested in looking at it as a specific object type which isn't defined in the current module it's in. Well, luckily you can scope what class you're interested in for the object that you're looking at. As you can see from the bottom part scoping here, again it uses this curly bracket style of scoping, which is curly bracket comma comma foo.dll, which is where the definition of the class that you're interested in is. And then back to scoping the object by star, which gives it the current scope, where you've currently stopped, of the object. And that means that you can cast things from different types that exist in different X's, which is really handy for, you've got many DLLs and many types defined. Again, you must remember that the debugger doesn't know about type defs. If you're unsure about what type an object is, you know, if you've always thought of it as cfoo_putter, which is really a type def, what you can do is go to the watch window, right-click on the variable that you're interested in once you've typed it in, and select the properties for that variable. And you get a small dialog that comes up and says, this is what the debugger says the type of your object is. The modules window, which is a new addition in VC6, I believe. You can get to that from the debug modules menu. And it allows you to figure out a few things about your app, which could be going wrong. Obviously, it lists the module name, but also it lists the address range that that DLL has been mapped into. And this is really good if you've crashed and you're not quite sure about which particular location you've crashed in. You can quickly look up where the EIP is by sorting the module list by the address range in which it's loaded into. Also, we show the full path of the DLL that's been loaded in. This is really handy when you may have many versions of a particular DLL that all have the same name, and perhaps an older one is getting pulled in from a path from a place that's on your path. So again, you can sort by full path and see, oh, my old path happens to be at the front of this module, so I have the wrong DLL here. And it also shows you the load order, so you can look at specific issues to do with that. So, debug works, release doesn't. That's never happened to me. But whatever you do, don't ship debug. What you'll find is a lot of the things to do with release, again, are because the optimizer is so unforgiving to you. Uninitialized variables, for example, can often be set to 0 in debug builds, but are just random stuff in retail. And what you can use is the compiler switch /gz. Now, gz means enable runtime checking. Now, this runtime checking allows you to check arguments that are passed in and out. It checks what the calling conventions are as well, and some heap checking as well. I've also got listed here, under overruns of memory, use the debug heap. Well, when you launch a program under the debugger, it's actually using the debug heap. So what you need to remember there is to watch out for using the debug heap. You should attach to the process as it's running, and that'll give you the heap that it actually runs as in retail. So remember, Optimizer is really unforgiving. The locals are overwritten all the time, and they're packed really tight. So if you're using things again, if you're overrunning, you're likely to hit things that are packed tight together. And the best thing to do is look at the disassembly. It's going to set you free. Again, it works when I don't use the debugger. So, like I say, NT is using the debug heap under the debugger to try and track bad allocations and so on. So attach to the process to make sure you get the process as it is running, as it would normally run, as opposed to how it would run in the debugger. Other issues that you get under the debugger are timing issues, specifically thread timing. But the debugger takes some time to respond to some events that are coming in from your program. Say module loads, we react to those. Creation of threads, we react to those. Unload of modules. Debug strings, if you're using output debug string or any libraries that you're using or output debug string, we take time to process those. And those all go into how the timing is affected in the debugger. And also, although I've got path may be different, the actual whole environment that you're running your debugger in could be different from what you're running your app in normally. So use the get environment string, just add a call to that in your app, and then you can dump out what that returns in the debugger and make sure it matches what you expect to happen as your app runs normally. So timing code, we've got a simple way of doing some profiling in the debugger, and that's to use these undocumented pseudo registers of @CLK. So what to do is, when you want to time how long a particular call takes, you can add these two watches, @CLK and @CLK equals 0. Of course, what that does is prints out the value of clock and then evaluates the second one and resets it to 0. So once you've typed those in, press F10, you'll be stepped over the function that you were interested in, and these two watches will be updated, and @CLK will show you the step time in nanoseconds. However, you have to remember, again, it's pretty simple profiling. It's going to get hit by all the same timing issues that I was just talking about on the last slide. So output debug strings, exceptions, and module loads, etc., etc. Edit and continue. This is a very useful feature. I tend to use it a lot myself. And what you need to remember about edit and continue is, even if you don't use the Visual C++ project system, edit and continue still works. It works on any build that you do. And that's because the symbolic information carries all that the debugger needs to ask for an edit and continue to happen. Be wary of editing lines that you're currently on. If you've actually stepped to a specific line in the debugger and you say, oh, this line's wrong, I need to change this variable here, you should probably set the next statement to be the one, the statement previously if you can, because you don't want to try and edit lines that you're currently on. Sometimes the edit and continue will fail then, saying, look, I can't mess with this memory. You're already messing with this memory at the moment. You've hit a breakpoint or you've stepped to this point. Also, if your build process actually moves DLLs from where they were built, so it's pretty common to build in one particular directory, deploy in another, and debug in that deployed scenario, the auto relink that happens with edit and continue won't copy. So that means you're stepping through your DLL, you decide to edit and continue, and only the DLL that is in your memory map space has changed. The one that's back in the original location, the one that's in the moved location has not been updated. The one that's back in the original build location has. So you have to watch out and do the copy again. And you could have, if you're not happy using the ENC that we already provide, you can do some ENC of your own by knowing, again, a bit of x86 assembly. If there's a piece of code that you're not interested in, you don't ever want to run this particular piece of code again, then take the code, go to the instruction pointer in the memory window, and that'll give you a dump of the memory bytes for that particular routine. And then you can select out the region of code that you're not interested in and fill it with 0x90 NOP. And it'll never ever bother you again. Also, if you want to switch the way an if statement works around or something like that, you can swap the opcodes 7.4 and 7.5, which will change the flag value jump if equal to jump if not equal, and vice versa. Pointers as arrays. Now, I'm sure you're like the rest of me, and you pass huge big chunks of things as a pointer to the first thing, and you happen to know what number there are, so you can iterate around them quite easily by using pointer plus x as the particular location. But the debugger's not very smart. It doesn't really know that. However, we do have an undocumented feature which allows you to specify that. So I'll quickly show you going back to the Scotsman demo. So we're back to the Scotsman demo. And you can see here that the way I'm declaring the collection of Scotsman is as an array of Scotsman stars. And further down the code here, I ask this collection to go have a drinking match, and I ask this collection to change a light bulb. So we'll step through here, and you'll see exactly what I mean in the original case. Change the exception state to not bother me with that exception anymore. Not bothered about that anymore. So we'll forget about the drinking match. That's all finished with. I finished with that last night, or maybe tonight as well. And we'll ask the Scots to go and change a light bulb. And when we step into this, again, we have just this folk variable, which is a pointer to pointer to Scotsman. And when I expand this, well, I get the first Scotsman on the list. Not particularly interested in them. I really want to see them all. So what you can do, however, is ask the debugger to treat that as an array of 4. This time when I expand it, I get the full list, which is very useful in the mega case. And this is particularly useful if you have large arrays. I think I'll show you this slightly differently here. Just delete this one. Oops. Guess who can't type today? Too much beer yesterday. So this time, I didn't check this out right enough, but what you can also do is ask the debugger to look at a pointer value that's way past the original value. So you can look at folk plus 2, folk plus 10, folk plus 1,000,000 if you're very interested in them, and then print out a certain number of elements at that location. So as I see here, pointer to 2 plus 2,000, and get the last 10 that are at that 2,000 location, which is really useful. Like I say, I do it all the time as well. I pass big collections as pointers to pointers, and this is really useful to understand what's in those arrays. So, have I gone back to the pointer? Have I gone back to the PowerPoint here? Not yet. Don't ask a debugger dev to work AV stuff. So, I'll go back to that again. As you can see, the bottom line here explains how to do the large case. To bracket out the new pointer location, if you're interested in one that's way beyond, and then I want the 10 elements that start at number 2,000. So I'll move on to disassembly tricks. So when you're at a particular piece of code, and you're debugging through it and you step to a particular location, you may want to go and have a look at the disassembly for that function. However, there's cases where you perhaps have a DLL that has managed to get compiled with the file name, 2 file names that happen to share the same name, or you're in a templated function, in which case you've got this source location, foo.cpp12, but it manages to map to many different instruction addresses. So when you ask for that, the debugger says, well, which one do you want? I'm not very intelligent, tell me where you want to go. But if you're interested in the one that you're specifically at, just pick the top one, and then when you've gone to the assembly window using Control G is automatically set up in disassembly to go to the address. So you can quickly type EIP, which is instruction pointer register, and that'll take you to the exact address of the one that you're actually located at. So Unicode tricks. It's compiler's fault. All of it. It's all the compiler's fault. It's nothing to do with the debugger, I promise you. So the compiler emits B stars, OLE stars, WCAR_Ts as unsigned short stars, which is really useful. You can really differentiate those. But we have a workaround in the debugger. You can go to the debug tools options debug and click the checkbox which says expand Unicode strings by default. And this turns everything that's an unsigned short star, even if you're not interested in Unicode, into wide strings. Or in the watch window, one of these comma subscripts, you can use "SU" to force a Unicode display on a specific variable. Finally, if you're looking at a big chunk of memory and you're interested in what the Unicode values are in that, there's also a wide-car format. You need to go to Tools, Options, Debug, Format, and select wide-car, which is about the second one down for the memory view. You got to watch out for if you want to display Unicode things, it could be that the font the debugger happens to be using at the time does not have support for that Unicode character. So I can highly recommend getting the MS Arial Unicode one, which has the full set of Unicode characters. It doesn't matter from whichever, and that will show you everything that's in Unicode. So remote debugging. Remote debugging is very handy in a lot of situations where you can't interfere with what's happening on the screen or something like that, and you want to leave the other machine as clean as possible. So it's not really hard to do remote debugging to set up. There's reasonably good docs. But if you spend a little extra time in setting it up, you can make your life a lot easier. So first of all, of course, on the local machine, you do your builds, and then share out the directory to your application from your local machine. When you've shared that out, do a map back onto your own machine of a specific drive letter. And this is going to allow you later to share the same letter on the remote machine as you have on the local machine. So set up for remote debugging by go to build remote, ask it to do native TCP IP, and change the machine name to the machine that you're going to be doing the remote debugging on. Also in the project settings dialog, you need to then fill in the remote path of being this new map drive letter, O:, and then wherever your exe is built in there. On the remote machine, you just want to install MSVCmon, and the easiest way to do this is just install Visual C++ on that machine. But if you're worried you don't want to install the whole product, there is an article in the docs which tells you exactly which DLLs you need to copy across with the MSVCmon exe, which is our remote debugging agent. One thing you must remember, though, when you're doing a tiny, small remote installation for MSVCmon is that we need to have our MSVCRT in the system directory, the MSVCRT that ships with the debugger. So again, you map the share to the same letter that you mapped the share to on the local machine. So this means that O::foo.dll is O::foo.dll on both machines. And as normal in remote debugging, you launch the little debugging monitor MSVCmon, click on connect, forget about all the options, just go, and you're ready to go. Then to start debugging, you can do step and go, but you can't do remote attach. Then, I don't know if you've come across remote debugging before, as the debugger steps through and it gets module loads, it says, hey, where are the symbols for this particular module? It's remote, I don't know where I'm going to find the symbols. But because you've went to the trouble of setting them up to be exactly the same path on both machines, the default DLL path should be the right one. It should look at the same correct place. And that should make things nice and easy for you. So my final demo is a bit of COM debugging and how we've hopefully improved our support for that with a few extra add-ins that we've put in. Specifically, H results you can now view as the actual H result rather than the hex code number by using this .HR subscript. If you're interested in perhaps you use the result of COM calls in other functions, then you can use EAX HR, which will give you the return value. The return value is all stored in EAX, formatted as an H result before you step into another routine. Also talk about @err, which is our pseudo register for what the last Windows error was on that particular thread. Also, we do decoding of GUIDs and variants. Our GUIDs, we map them back to the exact class name that you've registered them as, and variants will show which union is currently selected for that variant. And the demo also shows stepping into across exe boundaries and doing a little ENC as well. So I'll swap over to that just now. So we have here two projects because we've got two exes. We have a COM demo client, which is going to co-create an instance of class ID test. The class ID test is implemented over here in this server. And the only method we're going to call on this object is getString, which returns stuff from here. So if we run this code under the debugger at the moment, I'll go back to the initial one. If we run this code under the debugger at the moment, we find that it stops at this assert. This particular implementation of assert figures out if you're running out under the debugger and says, okay, we got to stop. This assert failed. And what it's saying is that we've managed to, we've not got a success case for this last COM call that we did. So what exact failure case did we get? So we ask it to format that H result as an HR. And it says access denied. So we're going, okay, what's happened here? We're not quite sure about what's happened. We need to stop and go back and figure out, step into the call itself and figure out what happened. So, okay, it looks like we managed to co-create the class okay. There was no assert there. And I've stepped into some ATL glue code, which I should have used no step into for. And as I step in, I get access denied. And that is because I have not done this machine. I've not rebooted this machine since I was connected to the domain. So I'm going to cut my demo short here, actually, and reset it up, reboot my machine to get it reorganized and redo the demo. And in the meantime, I'll start possibly taking some questions. Or I could go over, although you didn't get handouts, which I'm really sorry about, I expected you all to have printed sets of my slides. I have some sample code which you can use when you're debugging your applications to help you use the debugger to the max. I have an implementation of break, which keeps all the stack frames that you're interested in, checked cast, verify COM interface, a new assert to add to the many millions, verify bster and verify right pointer. So does anybody have any questions? Should we just go into the questions just now, and I can leave you to look at the sample code yourselves? So if you've got questions, perhaps you can step up to the mic and possibly other people can hear them. Thanks all for coming, all those people that are heading out anyway. Thank you.
Hello there.
Hi there.
Could you tell me where we could possibly get a list of all those comma options?
Well, the comma options, sorry, the question was, that for those of you who didn't hear, people were asking, where can I get a full list of the comma options that are the format specifiers in the watch window? So the answer is autoexp.dat contains a list of all those format specifiers that are usable by you to format your strings so that it can format specific chunks of your code to the style that you want. So you'll see a full list of them there: ST for string, SU for Unicode, and octal, binary. You name it, it's there. So you, sir?
Hi.
How you doing?
Good. I have a COM object, and it's running under MTS. I'm getting a 4129, which is an exception. Now, normally in the past, I'd use ATL trace and go into all the functions in the object and say entering function, leaving function, till I find out what function it was and then step through it and find out where the problem is. Is there any easier way to get there?
So I think you were saying that the question was that there was an exception raised in your in a COM object. The exception was raised in the COM object,
right?
And you want to figure out where it was thrown from. Is that right?
Yeah.
So hopefully, what I was saying about stopping on the exception rather than catching it in the exception handler, is that not?
Doesn't work because it's in.
Is this specific to MTS, possibly?
Yeah, it's in Viper. It's in the MTS module itself.
Right, so the exception is raised in another exe, and you want... I'm possibly a bit confused. Maybe we could take this one offline, and I'll discuss it in more detail with you. I'm going to go to coffee anyway, and I'll treat you to a latte afterwards. So back to this side. How you doing?
Good, how you doing?
Good.
If you have a COM object that I want to look at all the members of that object, like you did with the array earlier, you put in the comma 4, you're able to see the elements in the array.
Mm-hmm.
If I wanted to look at all the members inside of my object, similar to what you do in the VB immediates window, if I have a variable of type, Scotsman, and I drop that into the immediates window and I expand it, I can see all the members of that.
Mm-hmm.
Is there a way to do that in the C++ debugger?
So, possibly I didn't explain this quite so well enough. The gentleman was asking if there's a way to see all the member variables of a particular object. So, if I go back to Scotsman demo here. Now, as a COM object in particular you were interested in, now, being able to see the member variables of a COM object is specific to how you have a pointer to that COM object. You have a pointer to an interface more than likely. Right. So the only way you're actually going to see the member variables of the object on the other side is to step into code on the other side. There's not enough information in that object because we only have an interface pointer. That only tells us what the vtable looks like on the left-hand side. And that's all the type information for that local variable that the debugger has. Mm-hmm. You could possibly cast it if there's not been marshalling going on from side to side. The marshalling will add some stuff around the object. So S1 here is not enough for you if you've only got an interface pointer. But if you're able to step into the object on the other side, into one of the methods, you should be able to expand all the variables for it.
Okay.
Does that cover it?
Yes, it does.
Okay.
Thank you.
So on this side, how you doing?
Hi, good. I have a question regarding remote debugging.
Remote debugging.
When you attach to the remote machine using an IP address, is there a way to know the port number or specify the port number in case you're behind firewall?
Not as yet, I'm afraid to say, no. Port numbers are we start at a specific port for that. Sorry, the question was...
By the way?
Sorry?
Are these documented anywhere? Because I couldn't find them.
They are undocumented. Again, if I could take this one offline with you and we can discuss it further later on. So the gentleman was asking if the port number for the remote debugging was documented, but that's not the case. So back on this side, how you doing?
Good. I just got a simple question. We were just wondering about the CD you mentioned, where we can find that.
Sorry, I missed that.
The CD you mentioned for the source code and the PowerPoint
well,
and all that.
Do you not have a CD with all the PowerPoint slides?
Nothing. No.
All right. I think that's posted out after the event. I'm sorry. That's
okay.
Right. It's because they held it out for things. I'm really disappointed they didn't actually give you printed out ones from mine, because that's how I've done all the talks before. If you're interested, I can give you a quick rundown. Is anybody interested in having a look at the sample code that I've got? Right, okay, so I'll take these last two questions and then we'll go over the sample code that I have available, okay? So back to this side, how are you doing?
Pretty good. Are there any plans to release updated symbols for Windows 2000?
So symbols should be available for Win2K, is that not correct? I believe they're available via NT's website rather than ours. But I'll check that out. If you grab me at the end, I'll grab your email and double check on that for you. I'm not 100% sure.
Cool.
Yeah, that's right. A full MSDN will come with that.
Yeah,
How you doing?
Fine, thanks. We have one applications we use like Microsoft OCX. It runs fine if you install the Microsoft Video Studio, but we install other PCs, scratches. How do you debug that?
How do you debug things where you've just installed a scratch machine, something fails over here, and you don't have a debugger? Well, remote is probably your best option then. You want to look in the Visual C++ documentation that will give you the exact small set of DLLs and exes for MSVC Mon to install on that remote machine, and then run the application that is calling that OCX on your client, on your faraway machine, and that should be able to debug it. Does that cover that, or am I not quite with you?
I'm not quite sure.
So as I understand it, you have built an OCX that's distributed out on on another machine, and the client is also running on that other machine as well. Is that correct?
Yes.
Yes. And you're interested in debugging that OCX.
Right. It seems fine if the client machine has the Video Studio installed, even though you install nothing. I can run the applications.
Right. Well, one thing you have to remember about OCXs is, like any other DLL, you've got to watch out for the dependent DLLs that they're dependent on. Are you sure that the versions of the DLLs that you have on your Visual Studio machine match the ones on the machine far away? So for the runtime is a good example. If you're building an OCX, you should distribute the runtime with that OCX and keep it in the same place, and it'll make sure that it picks up the right one for that OCX. These sort of cases are very similar to it works in debug and it doesn't work in release. It's usually to do with environment, to do with particular paths to particular modules. And the way you can check that out, as I say, is to use remote debugging and then look at the modules window and see which modules are actually loaded into the system, the full paths to them on that remote machine. Then use Explorer on that faraway machine, and that will give you the exact version numbers of all those modules. So hopefully that will get you going. If not, we can probably take this one offline as well, and you can come and grab me at the end, okay?
Okay, thanks.
Okay, thanks. So do I have one more over here?
Yes.
How you doing?
Okay. Got a situation where I'm attempting to load a service that runs on some machines but not others. Sometimes when the service loads on a specific machine, it comes out with an error. Is there any way to use the debugger to track what's going on and figure out how the machines differ?
So what you can possibly do in this case is, in some of my sample code that I'm going to go to, I have an instance of break, which does a debug break. Is your service run at startup, or can you run the service anytime? You can just start the service up whenever you want.
You can stop and start the service whenever you want.
Okay. So what you want to really do then is put a break at the very start of your service program, right? And when you've actually hard-coded that debug break into your service, it means that the debugger will get a chance to JIT that program. Mm-hmm. And then you can run it under the debugger in that case and see, is the path different? Is the environment different?
In this case, though, I didn't write the...
You didn't write the service?
I didn't write the service. I'm trying to figure out why somebody else's service isn't working on one machine and is on another.
So I don't think there's going to be an awful lot I can help you with there. Debugging is symbols really. And if you don't have the symbols for it, and you can't do too much debugging, unfortunately.
Okay, thank you.
Sorry about that. So last one over here. How you doing?
Pretty good. When I build a ATL ASP component and put into IIS. There are situations that I need to use on start page and on end page.
Sorry, you need to use?
On start page.
Okay.
Is there a way to step into on start page and on end page?
To step into on start page and
function, yeah.
Yeah. So the question was about being able to debug an ASP, an ETL component that's linked via ASP.
Yeah,
is that correct? Yeah. So the ETL component is built normal Visual C++, and the link to invoke that is via ASP in IIS or Internet Explorer.
IIS. It uses the object context.
Okay, so what the ATL component then actually lives inside the IIS exe. Right. So you want to attach the debugger to the IIS exe, and then set your breakpoints on the particular on start page that you're interested in, or your own implementation underneath it. And that way, when your component is loaded up, we'll be able to bind the specific breakpoint in. You also need to use the additional DLLs one for that to say, this DLL is going to load. Please, please bind breakpoints when it gets to there.
Okay, thanks.
So, any more questions? No? Okay, I'll do a quick run of the sample code that I've got. So, oh yeah, more info. If you're looking for more info about debugging stuff, there's a. Oh, could I be a B? Useless. Beg your pardon. Sorry about that. So, for more info, there's a public news group that we have, microsoftpublic.vc debugger. If you don't have NNTP access, you can use Deja News to access that. I can really highly recommend. You can see smattered throughout my talk is talk about disassembly this, opcodes that. Read up Matt Petrick's article, Under the Hood, MSJ, February and June 1998, which is just enough assembly language to get by. So a really excellent article. If you've always been mystified by what x86 is doing underneath you, this is an excellent article. And for those who don't already subscribe to MSDN, I can not recommend highly enough John Robbins' series of articles called Bug Slayer, which he talks about lots of debugging tips and tricks, and steals from this talk as much as he likes. So, back to where do you want to go today? To lunch, probably. I'll need to get to PowerPoint actually to view these slides. Okay. So the one you're probably all interested in is set thread name. Now, can anybody see that? Is that too small? Yeah. Too small.
Have you changed your slides since you submitted them to the people?
No.
Okay,
so the ones that are on the CD are the ones that have been on this machine. They're definitely the same.
Great, thank you.
Okay, I'll change the font size on this for you. Okay, sure. There we go. We'll just do some scrolling. Okay. So set thread name I talked about earlier in the talk. Here's the snippet of code that will be available in those PowerPoint slides. You can just copy and paste this into your own util directory, quite happily enough, and use it as much as you want. But the information structure that I declare here is ours, and if you mess about with that, then you might get bizarre consequences. So thread name info, you must have that set to COX1000. You have this SZ name, but again, it can only be 9 characters. Thread ID, which you can get from get current thread ID, and flags, which we're keeping for our own use. And then the set thread name routine basically raises an exception number with this particular exception number. So thou shalt not throw 2 nor 4, but thou shalt throw 406D1388, which is that highly rememberable number. So you definitely need the copy of the slides. And you can have this in your retail code as well, because it has an except block as well. It costs an exception hit, right enough, but it doesn't affect how your retail code will run. It will just continue on quite happily. The raise exception happens and we grab the exception, knowing that it's our number, unpack that structure that you've passed up to us, and set the thread name in the window due to that. So I don't know if any of you have used debug break. Has anybody used debug break at all? Okay, so debug break, it's common for debug break to make us lose a stack frame or so. So there's this macro is defined as asm_int3, which will just make a break happen without you losing all those stack frames. Asm_int3 obviously is specific to x86, so we call the system function as there. You'll see me do this do while around all of my macros. It's just a little trick to make sure that everybody calling the macros puts a semicolon after them, because sometimes you won't get compilation errors by omitting the semicolon sometimes if you don't use the do while. So it just forces people that are using this macro to be good citizens and use semicolons. So check cast. Check cast depends on the fact that you're going to use compile with runtime type information in debug builds, and it uses the dynamic cast, the new C++ dynamic cast operator in debug, and asserts that definitely returns a pointer, otherwise it would return null if the dynamic cast doesn't work. And back in retail, it just does a normal static cast, so you can expect that to just cast things. But what it does mean is that in debug builds, you'll get plenty of asserts if you are dynamic casting things to the wrong type. Verify COM interface, so really complicated and long macro template function, sorry, of addref and release, which of course checks to make sure that the COM object has a correct virtual function table. It's still valid. It's a templated function, so it doesn't matter what type you pass in, it'll always do addref and release as far as that COM interface is concerned, the correct ones. Verify bstar. So verify bstar basically is just checking that the length of your bstar is the same as the actual WCS length, which is the CRT's function to look at the length of any given pointer. There is one caveat with this, though, is that it doesn't work for bstars with embedded nulls, obviously. So I have an assert implementation here. Oops. Is this going to need to be a little bigger, is it? Can everybody see that, or is it? Can you see that up to the back? Okay. So this assert implementation, basically, it's quite similar to probably many other people's as well. It allows you to stick a debug string out to the debugger if it's present when you're doing when the assert fires. It does a break as well to make sure you hit that particular point. Otherwise, if you're just running along and you're running outside the debugger, it will message box you to tell you, I had an assert. It uses the file line macros from the compiler to tell you exactly which file and line, and it tells you the the assertion that failed as well, the particular one. And obviously it does nothing in retail builds. Verify right pointer. Verify right pointer is just a wrapper, a templated wrapper around is bad right pointer, which is one of the NT system functions. One thing to remember about verify right pointer, however, is it's not thread safe, in that is bad right pointer simply reads out from that address a particular size and then writes some information to it and then puts the old information back in. So you can expect if you use that in a multi-threaded environment, you're going to end up with problems. And that's me for today. So hopefully that's given you some more info with those samples. Thank you. So people that I said we need to take these conversations offline, I really need some coffee now. So if you want to grab me, we'll go get a coffee. And that includes everybody who wants to come for a coffee. Sorry? Oh, I forgot the punchline of the joke. So how many Scotsmen does it take to change a light bulb? Well, the answer is none, because they're all too busy drinking.